What would you do if a spacecraft older than most of the people operating it suddenly called home from beyond the solar system, and the message made no sense? The signal did not vanish. It arrived from the darkness, carrying a problem hidden inside a stream of broken data that engineers had to solve without touching the machine. Before we follow that signal into interstellar space, tap like, subscribe, and share this video with someone who thinks old technology is useless. Voyager 1 is about to prove that the oldest machine can still ask the newest questions. Voyager 1 was never supposed to become a legend. In 1977, NASA launched it for a short tour of the outer planets. The original plan was simple by space mission standards: fly past Jupiter and Saturn, collect images and measurements, and then continue into the cold beyond. Nobody designed the spacecraft for nearly half a century of service. Nobody expected it to become the most distant human-made object ever built. And nobody could have predicted that its most important discoveries would begin after the cameras were turned off. Today, Voyager 1 is not exploring a bright planet with rings or a moon covered in volcanoes. It is traveling through interstellar space, the thin region between stars. It is more than 15 billion miles from Earth. A radio message takes more than 22 hours to reach it, and another 22 hours or more to return. A command is not a conversation. It is a decision made today, delivered tomorrow, and judged almost 2 days later. That delay changes everything. On Earth, an engineer can test a repair, see the result, and try again within seconds. With Voyager, every experiment is a long wager. A bad command might not reveal itself until the next day. A second mistake can consume another day. There is no technician waiting beside the spacecraft. There is no spare computer in a warehouse. There is only a fading signal, an old instruction manual, and a team trying to reason across a distance that light itself cannot cross quickly. The strange episode began in late 2023. Voyager 1 continued transmitting a radio carrier. That detail mattered. The spacecraft had not simply disappeared. Earth could still hear its steady tone, like an open telephone line. But the data riding on that tone was unreadable. Instead of clean engineering measurements and science reports, the flight team received a repeating pattern that looked like nonsense. The difference between a carrier and data is easy to miss, but it is the heart of the mystery. The carrier says, "I am here." The data says, "Here is my temperature. Here is my power level. Here is what my instruments detected." Voyager was still saying the first thing, but it had lost the ability to say the second. Engineers knew the spacecraft was alive, yet they could not understand its condition. That is a terrifying situation for a machine in deep space. A safe mode would have offered a clue. A total loss of signal would have pointed toward power, orientation, or hardware failure. Instead, Voyager appeared to be operating normally while its words had been scrambled. It was not an obvious shutdown. It was a voice that remained audible but no longer carried meaning. The team began with the Flight Data System, or FDS. This was not the spacecraft's only computer, and by modern standards it was astonishingly small. But its job was essential. It gathered readings from the instruments and sensors, organized them, and prepared them for transmission. If the FDS could not assemble the information correctly, the radio system could send a perfect signal and Earth would still receive garbage. The team needed a memory readout. In March 2024, they sent Voyager a command asking it to reveal what was stored inside the FDS. The request crossed the distance in roughly 22.5 hours. The answer took another 22.5 hours to return. While the engineers waited, they could not rush the spacecraft or ask a follow-up question. The probe had to complete the command on its own. When the readout arrived, it pointed to a tiny failure with enormous consequences. About 3% of the FDS memory had been corrupted. A single chip responsible for storing part of that memory appeared to have failed. NASA could not determine whether radiation had damaged it or whether decades of continuous operation had finally pushed the component beyond its limit. Either way, the result was clear. A small dead region contained code needed to format the spacecraft's information. 3% sounds insignificant until you understand where it was located. Imagine removing 3% of the instructions from a recipe, but those missing instructions tell you how to combine every other ingredient. The kitchen may still have food, tools, and power, yet the final meal becomes impossible to recognize. Voyager still had sensors taking readings. It still had a radio system. It still had electrical power. What it lacked was a working path between those pieces. The engineers could not replace the chip. They could not rewrite the entire computer from scratch. They had to work around the damaged memory. The affected code had to be divided and moved into available locations. References inside the software had to be changed so the separated pieces could still find one another. The team was effectively renovating a tiny digital house while the house was traveling between stars. This kind of repair sounds routine when described in one sentence. Move the code, update the addresses, send the patch. It was anything but routine. The software was written for hardware from the 1970s. The team had to protect memory that was still working, respect the limitations of an ancient processor, and make sure the new arrangement would not interfere with other functions. There was no convenient emulator that perfectly reproduced every detail of a computer built almost 50 years earlier. Then came the most uncomfortable part. They had to transmit the patch before they could know whether it worked. On April 18, 2024, the team sent the first section of the modified code. The command traveled through the deep space network, reached Voyager more than 15 billion miles away, and waited inside the probe. The spacecraft executed it. Then the team waited for the answer. On April 20th, readable engineering data returned. For the first time in about 5 months, the team could see the spacecraft's health and status again. The repair had not restored a damaged chip. It had taught Voyager to live around one. Additional commands gradually restored science data from the instruments that were still operating. The machine had not become new. It had become adaptable. If this kind of problem solving is why you watch space stories, leave a like now, but do it for the engineers who had to make every command count. And if you are new here, subscribe before we follow Voyager into the next crisis, because the memory repair was only the beginning. The next threat was not inside the computer. It was in the spacecraft's ability to point its antenna at home. Voyager does not need to turn like a car. It only needs to keep a narrow radio beam aimed at Earth. That sounds simple until you remember that the spacecraft is drifting through space, the planet is moving, and the probe must use tiny thrusters to make precise corrections. If its antenna slowly wandered away from Earth, the signal would weaken and eventually disappear. The spacecraft uses different thrusters for different motions. Some control the gentle movements needed to keep the antenna aimed at Earth. Others manage roll, the rotation that helps the star tracker maintain its reference. On Voyager 1, the primary roll thrusters had been considered unusable since 2004. Two small internal heaters had stopped working, leaving fuel lines too cold for reliable operation. Engineers switched to backup thrusters and moved on. At the time, that choice was sensible. Voyager had already exceeded its planned mission by decades. A backup seemed sufficient, but the backup thrusters were now showing signs of clogging. Residue from the fuel system was restricting flow. If the blockage became severe, the spacecraft might lose the ability to control its roll. The antenna could drift, and the most distant conversation in human history could end without warning. The team faced a deadline. The Deep Space Network antenna, called DSS-43, located near Canberra, Australia, was scheduled to undergo upgrades beginning in May 2025. The 70-meter dish could still receive Voyager's faint signal through the outage, but it was the only dish with enough power to send commands to the probes. Engineers needed to revive the dormant thrusters before that commanding window closed. Reviving them was risky. The old heaters might still be dead. The circuits might behave differently after 20 years. The software that controlled the movement had been designed for a spacecraft that was young, not a machine whose parts had endured decades of cold, radiation, and vibration. A badly timed thruster firing could create a new problem instead of solving the old one. The team studied the wiring and the history of the failure. They developed a theory that the heaters might not have been permanently destroyed. A change in the power control circuits could have left them effectively switched off. If the switch could be returned to its earlier state, the heaters might warm the propellant lines again. But Voyager's own protection routines added another layer of danger. If the star tracker drifted far enough from its guide star, the long dormant thrusters could fire automatically. If the heaters were not ready, the cold lines could make that firing hazardous. The engineers had to align the spacecraft carefully, send the commands in the right order, and trust a sequence they could not watch in real time. On March 20th, 2025, they sent the instructions. Then they waited. More than 23 hours later, the team saw evidence that the heaters were warming. The old system responded. A set of thrusters that had been considered unusable for 2 decades was available again as a backup. That moment did not erase the danger. It bought time. Voyager still had a shrinking power supply and aging electronics. The active thrusters still needed monitoring. The antenna still had to stay pointed toward Earth, but the probe was no longer relying on one increasingly fragile option. A forgotten pathway had become part of its future. The story is easy to frame as a battle between NASA and broken hardware. The deeper story is a battle against assumptions. Engineers assumed a memory chip had failed permanently, then discovered software could route around it. They assumed old heaters were gone, then found a possible electrical explanation. They assumed a 4-year mission would end long before the year 2025, yet the spacecraft kept forcing them to revise what old meant. While the team was saving Voyager's ability to speak and point home, the spacecraft was continuing a scientific journey that no replacement probe has repeated. In August 2012, Voyager 1 crossed the heliopause, the outer boundary of the Sun's protective bubble. The heliosphere is created by the solar wind and the Sun's magnetic field. It is not a solid wall. It is a shifting region where the Sun's influence fades. Crossing it did not mean Voyager left the solar system in every possible definition. It meant the spacecraft entered the interstellar medium, the space between stars beyond the heliosphere. Before the crossing, scientists had models of what that region might look like. The models were based on theory, observations from Earth, and indirect clues. No instrument had sampled the plasma there directly. Voyager changed that. It found a boundary more complicated than a clean dividing line, with magnetic fields, particles, and waves interacting in ways researchers are still studying. The plasma wave instrument produced one of the most intriguing results. In 2021, Cornell researchers described a faint, persistent hum in the interstellar gas. The signal was not a dramatic burst. It was narrow, weak, and steady. It appeared in data gathered over years, including periods between major disturbances caused by solar activity. Calling it a hum does not mean Voyager recorded a sound that human ears could hear in space. Space is not an atmosphere carrying ordinary sound waves. The instrument measured oscillations in plasma, charged particles responding to electromagnetic forces. Researchers translated the pattern into a form people could describe as a tone because the signal was continuous and remarkably regular. That quiet signal mattered because it gave scientists a way to track the thin material around Voyager without waiting for a powerful solar eruption. When the sun sends a shockwave outward, Voyager can detect how the disturbance moves through the interstellar environment. But the persistent emission offers something different, a baseline. It is like hearing the background noise of a room before someone opens a door. From those measurements, scientists can estimate the density of the interstellar plasma along Voyager's path. The spacecraft is not merely taking one snapshot. It is moving through a vast region and reporting how conditions change from one location to the next. Every new measurement adds another point to a map that cannot be drawn from Earth alone. The magnetometer adds another perspective. It measures the surrounding magnetic field. Together, the magnetometer and plasma wave system help scientists study how the sun's bubble meets the galactic environment. The boundary is not just a line Voyager crossed once. It is a region shaped by pressure, motion, particles, and magnetic forces. That is why the remaining data is so valuable. Voyager's cameras have been off for decades. There are no fresh pictures of distant worlds coming home. The spacecraft is now doing something less visually dramatic, but scientifically rare, measuring the environment between stars from inside it. A weak number in a transmission may tell researchers more about the structure of our cosmic neighborhood than a spectacular image ever could. And because the mission has no twin replacing it at the same location, a lost measurement cannot simply be collected later. There is no second instrument waiting nearby. There is no quick launch opportunity. The next spacecraft built to study interstellar space directly may take decades to arrive. For now, Voyager is the only witness moving through that darkness. If Voyager's signal has taught us anything, it is that the most important discovery may not arrive as a dramatic message. Sometimes it comes as a tiny change in density, a weak magnetic shift, or a repair command that finally produces readable numbers. Share this video with a curious friend and let them know that exploration is not always about reaching a destination. Sometimes it is about keeping one fragile witness alive long enough to describe where it is. Keeping that witness alive requires painful choices. Voyager's power comes from radioisotope thermoelectric generators, or RTGs. They use the heat released by decaying plutonium-238 to produce electricity. Unlike a solar panel, an RTG does not need sunlight. That made it ideal for the outer solar system and interstellar space. But its output declines with time. The decay is slow and predictable. The spacecraft loses roughly 4 watts of electrical power each year. 4 watts may sound tiny, but Voyager was never carrying a large modern power system. As the available electricity falls, every heater, transmitter, computer, and instrument competes for a smaller supply. A radio signal crossing billions of miles already demands careful management. Heating fuel lines demands power. Science instruments demand power. Even survival has a cost. The mission team created an order for turning things off. The decision is not based on which instrument is most famous. It is based on scientific value, power use, condition, and the spacecraft's changing environment. The cameras were shut down long ago because they could no longer return useful images at such a distance. Other instruments followed as their performance declined or their power became more valuable elsewhere. In February 2025, Voyager 1's cosmic ray subsystem was turned off to preserve power. In April 2026, NASA shut down the low-energy charged particle instrument on Voyager 1 after an unexpected power drop during a routine maneuver. The exact schedule can change as engineers respond to the spacecraft's condition, but the principle remains the same. Sacrifice one capability to protect the mission's remaining core. The magnetometer and plasma wave subsystem are especially important now because they match Voyager's location. They can measure the magnetic field and plasma waves in interstellar space. Keeping them alive is about preserving the only direct measurements of a region that is otherwise unreachable. There is an emotional cost to each shutdown. On paper, it is a line in a table. In the lives of the people who work on Voyager, it can feel like turning off a part of a colleague. Each instrument represents a question the mission once asked. What do the clouds of Jupiter look like? How does Saturn's magnetosphere behave? What particles fill the space beyond the planets? Some questions have been answered. Others are now closed because the probe must spend its final energy on survival. Yet the spacecraft is not fading passively. Its team continues to search for ways to use the power more efficiently. A software strategy, sometimes called the Big Bang, has been discussed as a way to adjust how Voyager manages its remaining resources and possibly extend science operations. Any such change must be approached carefully. A software update on Earth can be reversed in seconds. A software update on Voyager may take nearly 2 days just to reveal whether the first instruction worked. This is the strange relationship between age and intelligence in the Voyager mission. The spacecraft itself does not learn like a human. It does not invent new repairs. The learning happens in the collaboration between old hardware and present-day engineers. A failure reveals a hidden possibility. A diagram from the 1970s acquires new meaning. A technician notices that a circuit may have behaved differently than everyone believed. The probe provides the evidence, and people on Earth reinterpret it. That collaboration is why Voyager's story is more than a nostalgia piece. The mission demonstrates a kind of engineering that modern systems often avoid. The spacecraft has limited memory, limited power, limited communication, and no physical access. Its designers expected constraints. They built systems that could operate for long periods, protect themselves, and accept commands from far away. Decades later, those constraints have become the source of the mission's resilience. Modern technology is faster, smaller, and more capable. A phone in your pocket has more computing power than Voyager's onboard systems by an absurd margin. But speed is not the same as endurance. Voyager was built for a narrow purpose and treated every resource as precious. Its software was compact. Its hardware was tested relentlessly. Its mission planners assumed that repair might one day be impossible, so they tried to make the spacecraft graceful under failure. That lesson matters for future missions. A spacecraft traveling beyond the planets may need to function for decades before reaching its most important destination. It may encounter radiation, communication delays, and power shortages. Engineers cannot design only for the first successful launch. They must design for the day when a component fails in a way no test predicted. Voyager also changes the meaning of distance. 15 billion miles is difficult to imagine because human experience is built around roads, flights, and orbital satellites. A direct radio link makes the distance measurable. The message Voyager sends today is already old when Earth receives it. The spacecraft's present arrives as our future. Engineers are always looking backward at events that happened almost 2 days earlier while trying to decide what to do next. In November 2026, Voyager 1 is expected to reach a distance of 1 light day from Earth. NASA gives the milestone as November 18, 2026, when the spacecraft will be about 25.9 billion kilometers, or 16.1 billion miles away. A light day is not a new region of space and does not create a physical boundary around Voyager. It is a way to express the delay. Light traveling at its maximum speed would need a full day to cover the distance in one direction. That milestone is powerful because it turns an abstract record into a human measure of patience. At 1 light day, a command sent on Monday may not produce a response until Wednesday. A team can spend a morning preparing a test, then wait through the next day to learn whether it succeeded. The spacecraft will be farther away than any object humans have intentionally sent, yet its connection to Earth will still be active. The date may pass quietly. There will be no flash in the sky. Voyager will not cross a glowing gate. Its transmitter will continue sending a faint stream toward a planet that is turning beneath it. But the milestone will mark how far a machine built in the late 1970s has carried human intention. Think about what Voyager has survived. It crossed the harsh radiation environment near Jupiter. It passed Saturn and continued into darkness. It endured decades of cold and mechanical aging. Its power source weakened year after year. Its memory developed a failure that made its data unreadable. Its thrusters lost heaters and later faced clogging. Instruments were turned off one by one. Still, the spacecraft kept a radio beam aimed at home. The signal scientists cannot explain is therefore not one mysterious burst hiding an alien message. That distinction matters. Headlines often turn complex measurements into a single dramatic sentence. Voyager has not sent proof of extraterrestrial life. It has not transmitted an unknown language. The real mystery is deeper and more useful. What is the interstellar environment doing, and what can a tiny, aging instrument reveal about it? The plasma hum is not evidence of a hidden civilization. It is evidence that the space between stars is not perfectly silent. The interstellar medium contains charged particles and magnetic structures. Even where matter is extremely thin, physical processes continue. Voyager is detecting those processes at a level that Earth-based instruments cannot sample directly. The damaged memory episode also deserves the same honesty. Engineers did not perform magic. They read the symptoms, requested a memory dump, identified a likely fault, redesigned the software, and transmitted the repair. The achievement feels miraculous because the conditions were so unforgiving. But the miracle was made from careful records, patient testing, and people willing to question an old diagnosis. That combination, wonder without exaggeration, is what makes Voyager compelling. The probe does not need an impossible secret to matter. Its ordinary data is extraordinary because of where it comes from. A number measured in interstellar space can reshape a model of the heliosphere. A temperature reading can reveal whether the spacecraft is healthy. A working heater can extend the life of a mission by months or years. The final phase of Voyager will probably not have a single dramatic ending. It will be a sequence of decisions. Another instrument may be turned off. A transmitter setting may be adjusted. A computer fault may appear. A signal may become weaker. Engineers may recover one function and lose another. Eventually, the available power will no longer support the instruments or the transmitter. The spacecraft will continue coasting, but Earth will no longer hear its measurements. When that happens, the silence will not mean the mission failed. Voyager will have completed a journey far longer than the one it was designed to make. It will have visited the giant planets, crossed the heliopause, measured the interstellar environment, and shown that old hardware can be kept useful through ingenuity. Its end will be a limit of energy, not a judgment on the value of the mission. And there is something else worth remembering. Voyager carries the golden record, a small archive of sounds, images, and greetings from Earth. It was created when the spacecraft began its journey, long before the internet connected billions of people. The record was not a practical instrument. It was a message about who we hope to be. The probe's science and its symbolic cargo traveled together. Now the direction has changed. In 1977, humans sent Voyager away with questions. Today, Voyager sends answers back. The answers are faint, delayed, incomplete, and sometimes broken. But they arrive. They tell us how plasma behaves beyond the sun's bubble. They tell us how a spacecraft is aging. They tell us that distance does not automatically end a relationship between a machine and the people who built it. So when the next signal arrives, the team will not hear a voice in the usual sense. They will see packets of data, temperatures, voltages, counts, and wave measurements. But behind those numbers is a story. A spacecraft is still out there. Its memory has been rearranged. Its old thrusters have been reconsidered. Its power has been rationed. Its instruments are fewer, but the questions they ask have never been more important. If this story made you see Voyager differently, write "still listening" in the comments. It is a small phrase, but it captures the whole mission. A machine built for 4 years, still listening and still being heard nearly 5 decades later. Subscribe if you want more stories where science is not only about discovery, but also about persistence. The most moving part of Voyager 1's story is not that it traveled farther than anything else. It is that the spacecraft keeps making the distance matter. It transforms an invisible region between stars into measurements. It transforms a failing chip into a lesson about repair. It transforms a weak thruster heater into a reason to keep trying. It turns a slow decay of plutonium into a countdown that scientists meet with planning instead of surrender. One day, the signal will stop. There will be no final engine burn, no explosion, and probably no cinematic farewell. One last packet will cross the darkness. After that, a machine carrying a record of Earth will continue moving through the galaxy, but it will no longer report what it sees. Until then, every transmission is a narrow bridge between two places. On one side is Earth, crowded with people, questions, and changing generations. On the other side is Voyager 1, small, cold, and impossibly far away. The bridge takes nearly a day to cross. It can break inside a memory chip. It can weaken when a power source fades. It can disappear if a dish turns away. Yet the bridge is still there. And that is the signal scientists are watching. Not because it promises aliens, and not because an old spacecraft should be immortal, but because it proves that human curiosity can survive distance, delay, failure, and time. Voyager 1 is not simply sending data from the edge of our reach. It is showing us what it means to keep reaching, and after the original plan is over. As long as that faint carrier holds, the spacecraft is giving the universe one more report from the place between stars. It says the space around us is active. It says the unknown can be measured. It says a damaged system may still have another path forward. And, in the most literal possible way, it says that something made on Earth is still out there, still moving, and still calling home.